All right, so yesterday we started a little bit on 4.3. And in particular, we talked about the idea of having a homogeneous second order differential equation that had coefficients that were actually numbers, right? Meaning they had constant coefficients rather than what we saw in 4.2, which was if we have non-constant coefficients, all right? And so yesterday we talked about this idea that with these homogeneous second order differential equations, if we have non-constant coefficients, then we sort of have to know a little bit of that puzzle before we can finish the rest of it, okay? And so this right here would maybe correspond, not 3, to section 4.2, okay? But in our context today, we're going to finish a little bit about our conversation of principle of superposition. And then we're going to get to the characteristic and auxiliary equation, talk about our 3 cases. All right, so this, as you are sort of starting to put all of the pieces together, the difference between the 2 sections is really in whether the coefficients are constant or not constant, right? And so we spent a little bit of time at the end of class yesterday trying to guess some solutions. And it was an interesting exercise because what it asked us to do is not just look at something like this as an equation to be solved, but really start to think about what a second derivative equals something is asking us for. And so we interpreted this to say, what function has a second derivative that is equal to 9 times the function? And we started to come up with a list. And of that, we noticed that the solutions all seem to be of this form c e to the plus or minus 3x. Now, we finished the end of our class yesterday by talking about the principle of superposition. And this principle of superposition says that if you have 2 solutions, then you know that the general solution is nothing more than the linear combination of the individual solutions. All right, so if you think back to linear algebra or Math255 here, that general solution is just going to be a linear combination of our solutions. And so what that means is if we were to take a look at the example we did yesterday with the numbers, we could even say that y is going to equal y1, or sorry, c1 e to the 3x. That's one of the solutions, plus c2 times, what do you think the second solution would be? Right? We said that c e to the plus or minus 3x is sort of the form of all the solutions. If we have e to the 3x as one of the solutions, what do we think the other one would be? Yeah, e to the negative 3x, right? Sometimes we forget that that plus or minus symbol is really there so that as mathematicians, we can be a little lazy and not write out separate ones. But this plus or minus is secretly disguising that the second solution is e to the negative 3x. Okay. And so this right here would be an application of the principle of superposition. Okay, so we said, hey, here's the general form. We know that it's going to be e to the plus or minus 3x, but we can say e to the 3x is our first solution and e to the negative 3x is our second solution. And then we can write the general one as a linear combination of those. Okay, now this method, this principle of superposition is actually incredibly valuable in a lot of your upper level differential equations classes, meaning that your goal will be, can I find one example or one solution, another solution, and another one? And once you find them all, principle of superposition says you just write them as a linear combination and then you're done. Okay, so this idea actually comes up quite a bit in those upper level math classes or upper level differential equation classes. All right. Now, one thing that I want us to think about is this question. Let me see my spacing. Okay, so is this question. What will solutions to some second order homogeneous differential equation with constant coefficients? So A will be a number, plus B is a number, plus C is a number. So if you have this second order differential equation with constant coefficients, and it's going to equal 0, right? So it's homogeneous. What will the solutions to something of this form look like? So that's really the question that we're going to be focusing on today. And so let's use the idea of verification all the way back from day one. Okay. So here's my hypothesis. My hypothesis is that all of our solutions are going to be e to some power. Okay, that is my hypothesis. And so I'd like us to see if we can verify this. Okay, so suppose all solutions are of the form y equals e to the r. So I'm going to call that whatever's happening in the exponent r. Okay, so rx. So in our question, we had 3x, but now I'm going to say, let's generalize it and call it rx. Okay. Now, if we wanted to verify that this is true, what other information do we need here? Like, how does that verification process work? You can type your answer in the chat. You can say it out loud, your choice. But let's make sure we know how that verification process works.
Couldn't we just find y prime and y double prime and then plug them in and see if it equals 0, right?
Exactly, exactly. So we have a y. We know what we can sub in there. But we also have to find our y prime and our y double prime to sub those in as well. Okay. So y prime will go here. And then y double prime will go here. And if all goes well, we should get 0. Okay. So we take our first derivative here. we're going to remember we need to use chain rule. We'll get r e to the rx. And we're going to take one more derivative and we'll end up with r squared e to the r. So we've got our y prime, our y double prime. We're going to go ahead and throw those into the equation, see what we get. And so we will get a r squared e to the rx plus br e to the rx plus c e to the rx. And we hope that equals 0. All right. Now, as I'm looking at this, I notice that every single term has an e to the rx. So I'm going to go ahead and factor that out. All right, so I go ahead and factor that out. E to the rx. An exponential function has one really important characteristic, and that is that it has a horizontal asymptote at y equals 0. In other words, e to the rx cannot equal 0. Like by definition of what we know about exponential functions, this first term cannot equal 0. Well, if this is going to be true, what do we know has to be true about this expression in the brackets?
Has to equal 0.
It has to equal 0, right? If one piece of this product cannot equal 0, then it must be true. This must equal 0. Okay. And this thing that must equal 0, this expression is our characteristic or auxiliary equation. Okay. So sort of snuck a little bit of a proof in there for you, but we're going to be learning about this characteristic or auxiliary equation. And where it comes from is that if you suppose this form of the solution and you try and verify that this is indeed a homogeneous equation, the only way for this to be true is if this expression equals 0. Okay. And so we're going to use factoring a whole bunch today. In fact, we're also going to bring back our good old friend, the quadratic formula, and use that as we move away from the backstory and more into the process. Okay. So that being said, let's take a look at the first situation. Okay. So suppose you have a differential equation. A y double prime plus b y prime plus c y equals 0. We know it's second order. We know it's homogeneous, and a, b, and c are constants. So this is second order homogeneous with constant coefficients. What we're going to do is, if you think about where these letters came from, our a, b, and c, when we got to our characteristic equation, this part that has to equal 0, it turns out those coefficients were the same ones as in the original differential equation. That's the cool part, because what we can do is take something that looks like a differential equation and say, we're going to borrow those constants for a moment, and we're going to write it in an auxiliary equation. Because in order for our solutions to be true, we know that this has to equal 0. All right. So the differential equation is the one where we have the primes and the double primes, but the characteristic equation or auxiliary equation is the one where we replace the primes and the y's with either the letter R, that's very common, or some textbooks prefer the letter M. Okay, so either a squared plus or AR squared plus BR plus C, or a M squared plus BM plus C equals 0. Okay, it's a personal choice whether you use R or M. That is definitely up to you. I just did want to present sort of the two most common ones that I've seen. Okay. Now, what are you going to do after you write this equation? We are going to solve that equation for our two roots. Okay. And so that might mean factoring, it might mean quadratic equation, but we should always start with the factoring, all right? Promise you I've never taken a math class where I don't need factoring. So we want to make sure we're really fresh with that skill. And if it turns out that at the end we get two roots, they are real numbers and they are different from each other. So R1 and R2 are not the same number and they're real numbers. So there's no I business going on, okay? So if the two roots are real and distinct, every single time we can say that this is the general solution, okay? So now when we're solving, we're going to be doing some algebra using that result and interpreting it to obtain our general solution. All right. And this is a pretty big theme in differential equations, is really like algebra on steroids. Like, how do we use all this stuff about algebra we know to help us solve these calculus problems? All right. So let's take a look at this first equation. It says solve the differential equation 2y double prime minus 5y prime minus 3y equals 0. All right. So if we look at our sort of to-do list, well, we have a second order differential equation, homogeneous with constant coefficient. And in particular, we might notice that A equals 2, B equals 5, and C equals 3. All right. What mistake did I just make?
T equals B is -5 and C is -3.
Yeah, we want to make sure we grab that sign in the front as well, okay? So when we're looking for the numbers, it's built into the equation that it's positive. So if there's any minuses, we have to account for those as well, all right? So if our coefficients are constant, then we're going to use this process, okay? So if we think about it in steps, we might say that we are going to write our characteristic equation. And in our case, for example 1, we would say that we have 2r squared minus 5r minus 3 equals 0. All right. You could write this as 2m squared minus 5m minus 3 equals 0. That's fine. But I would suggest to not use x because we're using x for something else. Once we write that characteristic equation, we are going to find the roots of our characteristic equation. So as I'm finishing writing this sentence, if you would go ahead and start factoring, that would be amazing. Right? And so let's see, when we factor, I think we end up with 2r and r. And we want to make -5, so maybe +1 minus 3. This should give us a -6r. and then a positive 1r, that gives us the negative 5r, and then positive 1 times negative 3 is negative 3. All right, so we've gone ahead and factored it, and we're going to find the roots. I know that you folks know how to solve these equations, right? This one pretty obviously is 3, but I've had some folks move sometimes too quickly on something like this, and they'll either get the sign wrong, or they'll flip the numerator and denominator. So just make sure you double check these, but we should get r equals negative 1/2 and r equals 3. Okay. Our third step will be to interpret and write a final solution. And we've only learned one case so far, and it's clearly under the section that says real and distinct roots, right? But when you look at your homework, this would be an important step to think about. And so when we're interpreting, we're thinking, are the roots real? Yeah, negative 1/2 and 3 are real numbers. And are they distinct? Yes, negative 1/2 is not the same as 3. And that means I can write my solution as a linear combination of e to the negative 1/2 x and e to the 3x. Okay. So that might look something like this. Y of x equals c1 e to the negative 1/2 x plus c2 e to the 3x. All right. And I always get the question, like, is it okay if I do this instead? And that's fine. Okay. Now, all that means is if you use the first variation, you will get some number for C1 if you were solving for it. And if someone else used the other version, their C2 would be the same as your C1. Right? So it's okay. It doesn't matter which root you put first. It just matters that you have them both represented there and that they're real and they're different from each other. Okay. All right, let's take a look at example 2. All right, so I would say that I am a big fan of factoring because I think that you need it so often that I like to have factoring problems. But that being said, I think it's important to look at ones that aren't, just so we brush up on that quadratic formula. All right, so I will sort of spoil the surprise that example 2 is indeed non-factorable, which would lead us to say we should probably use that quadratic formula. All right. So if we were to write our characteristic equation for example 2, what would we get? What would that characteristic equation be? Yeah, A is 1, good. B is -6, C is -2. All right, so we could say our characteristic equation is 1r squared minus 6r minus 2 equals 0. Okay, so we could write that. You don't have to write the 1, obviously, but in case you were wondering where that came from. And in this case, this does not factor. And so we're going to go ahead and find the roots using our quadratic equation. So embarrassingly enough, I think it was like when I was first becoming a teacher. So I used to teach high school, and you have to take like a test to show that you can do like this kind of stuff. And I stupidly didn't really study for the exam. I mean, I kind of looked over it, but I just figured it would be fine when I walked in. And there was a question about the quadratic formula and I couldn't remember the formula. So I had to like rederive it all, which is silly. But yes, since then I have remembered what that formula is. But we have our negative b plus or minus the square root of b squared minus 4ac all over 2a. And if you know the tune for Pop Goes the Weasel, there is a song that goes with the quadratic formula. I do not sing, so I will not be showcasing that, but you are welcome to sing through it in your head. Yeah, right? I know. I feel like that whoever taught you that, like there's just these things that stick with you for sort of a lifetime, and it's kind of neat. But here's our quadratic formula. And so let's go ahead and plug in our values. We get -6 plus or minus 36 minus 4 times 1 times -2 all over 2 times 1. And that will give us 6 plus or minus, let's see, 36 plus 8 is 44, right? 36 plus 8 is, yeah, 44 over 2. That's the other thing about sort of teaching all these math classes is somehow I am worse at my mental math now than I was like a long time ago. But here we have this. This one turns out to be reducible in that I could say this is really 6 plus 4, nope, case in point, 2 root 11 divided by 2, which makes it nice to write as 3 plus or minus root 11. Okay. Now, once you found your roots, then you can go ahead and interpret them and find your solution. All right. This is just like when we had like that plus or minus 3x, how we sort of secretly buried 2 solutions in there. 3 plus square root of 11 is different from 3 minus square root of 11. So they're distinct and they're both real. So we can, without doing any calculus, say that our solution is C1 e to the 3 plus root 11 times x, and then plus C2 e to the 3 minus root 11 times x. Right? So we've done 2 problems. We've been able to use a skill that we learned so long ago and use it to save us from doing any calculus and finding these solutions. Okay. So this unit tends to be pretty fun because if you are good at the factoring and you've done your, paid your due diligence and practiced all of that in the past, as long as you can interpret the solutions, then you're good to go. Okay. All right, let's try one more example. All right, this one will have our initial conditions here because I think that we should practice with those initial conditions. All right, so we'll maybe make a note here that these are our initial conditions, which means that we're going to do the steps like we did in the previous question, but at the end, we're going to have to add a step like 3.5 where we find values for C1 and C2. Okay. So let's go ahead and write our equation. And this one should give us 3m squared plus 2m minus 8 equals 0. I'm only using m to show you, you could use M also. It doesn't really matter what letter you use there, okay? I think it would maybe boil down to which letter looks least like a number when you're writing a bunch of these and you wanna make sure you don't mistake like a 6 for a B or something like that, right? This one does factor. And so I believe we've got 3m and m. I know I need to make a -8 at the end. So like 2 and 4 seem good to choose. 2 and 4. I want a plus 2m. So positive 6m minus 4m will give me 2m.
Hey, Judy.
Yeah.
Hey, I think I missed something. Why is it M instead of R?
So I only wanted to use a different letter because I set up here that some textbooks use R and some use M.
Oh, okay.
Okay, and it doesn't matter which letter you use, pick one, go with it. You could use all R's, you could use all M's, whatever is less like a number for you is fine.
Okay, yeah, thanks.
All right, so we've got this, we can solve, we can see that M or R equals a positive 4/3 and a negative 2. Okay. We're going to interpret and find a general solution. General meaning you still have C1 and C2 as variable or as like a letter. All right. And so we know because these are different 4/3 and negative 2, that we could write this as C1 e to the 4/3 x plus C2 e to the negative 2x. That would be one way of writing it. Or you could write it with your constants the other way around, meaning y of x would equal C1 e to the negative 2x plus C2 e to the 4/3 x. All right. And I'll leave that up to you. It's such a small piece, but I did want to let you know that like these could be equivalent expressions. But if you have the first one, your C1 will be the same as someone else's C2 because it's the number that goes with the e to the 4/3 x. And this C1 will actually be the same as that C2. Okay, but at the end, you should have the same answer. It might just be reversed in terms of which one plus which one. Okay. Now, since we have initial conditions, we have to apply the initial conditions. And I really want to emphasize here, you need to write out your final answer again, like all of this with a number for C and a number or C1 and for C2. So if you just kind of find C1 and C2 and you don't write it back in, you haven't given your final solution yet. Okay, so just make sure you sub those back in and you'll be good to go. All right, so what do we do with these initial conditions? Well, this first one, y0 equals -6, I can go ahead and plug that in to my general solution. Okay, so let's see what we get. So y of 0 equals C1 e to the 0 plus C2 e to the 0. Right, because 0 for the x is going to zero out the exponents. And so what do I end up with? I end up with -6 equals C1 plus C2. All right, so let me get this back, the whole question back on one page. Does that part make sense to folks? Where we got this -6 equals C1 plus C2. All right, I see some heads nodding. Okay. Now we have to use the second initial condition, right? A second order differential equation means that you get 2 initial conditions. This one, however, is not for y, it is for y prime. So what we're going to need to do is take our solution, take the derivative, and then plug it in. Okay. So my second initial condition means I have to find my derivative. I got a little bit of chain rule here. So 4/3 C1 e to the 4/3 x plus, let's go with the -2 C2 e to the -2x. So we take our derivative and now we plug in our initial condition. So we have y prime of 0 equals 4/3 c1 e to the 0 minus 2 c2 e to the 0. And we said from the question that equals negative 18. So I'm going to get a second equation that is negative 18 equals 4/3 c1 minus 2 c2. Okay. We've got a system of equations. This is like throwback to like middle school, right? We've got a system of equations. Now we need to find C1 and C2. Now you can use substitution, elimination, that's fine. If you want to use matrices, that's fine, okay? Just show me your thinking and whatever your process is. I think at the end, we end up with C1 equals, make sure I get this right. I think I get C1 equals negative 9 and C2 equals a 3. All right, but let me pause for a moment. And if anybody is computing these values, again, you can use the system of equations, or you can go ahead and use matrices because you just learned that in linear, right? So you can use whatever methods suit you for this. And let's see if we can confirm that answer that it is C1 equals negative 9 and C2 equals 3. Yeah, okay, we've got one confirmation. That is good. Right? Now, if you had chosen the other way of writing the general solution, then you would have just swapped your C1 and your C2, okay? But either way, when you plug them back in, because we want to box off a final answer, we would say y of x equals negative 9 e to the 4/3 x plus 3 e to the negative 2x. And this, my friends, would be our final answer. Okay, so let me get that on one page for you. All right, so solving this differential equation, we actually didn't use anything about calculus at all. All we did was a whole lot of like middle and high school level kind of work, but in a much more grown-up context. Okay. So let me pause here for a moment. Are there any questions that are arising for folks before we move on to the other two cases? All right. Well, it is always okay to think of questions later. I trust you to communicate with me in either Discord or Canvas if you have any questions, okay? All right, so that is one case, right? You find your characteristic equation, you factor, and you get two roots and they're real and they're different. Well, we also have to consider what happens when they are real, but they are the same. Okay, meaning that whatever you end up factoring, you get R1 equals R2. And so we just call that an R or M, okay? It turns out that if you have a second order homogeneous differential equation with constant coefficients, you can write your characteristic equation. You solve it, you get a repeated root. The general solution looks a little bit different, okay? It's so sneaky. I'm gonna highlight this in yellow so we don't miss the sneaky part. This part exactly the same as when the roots are different. That x is the one thing that makes it different from the distinct root case. All right, so let's make sure we are aware of that. That is the one thing that makes it different from the real distinct case. All right. Now, we won't go into the theory about where that comes from. But the short of it is, if you were to look back at our sort of secret derivation proof from a few pages ago, if we did that with the repeated roots, an extra x would pop out. Okay. But let's take the time to kind of practice this process, right? Because as important as conceptual understanding is, it's also important for us to make sure we understand the process. And so we can go ahead and take a look at this differential equation. We notice that all the coefficients are real. So we can write real and they are constant. And so we can write a characteristic equation that is r squared minus 10r plus 25 equals 0. And when we solve, we might already be able to tell this is a perfect square, right? We end up with r minus 5 times r minus 5. And so what that tells us is that r1 is the same as r2, which is the same as r, which is going to be 5. And so for our general solution, it would be important for us to remember, as we're writing that general solution, that because we ended up with the same number, we do not want to write this. This would be super sad. Okay, so we need to account for the fact that we have a repeated root. We want to make sure we don't forget that C2x e to the 5x. So again, this x must be in there in order for us to have a general solution if we have real repeated roots. Okay. All right, let's try another example. Okay, so we're going to try a different example, and this one also comes with initial conditions. So it'll give us a chance to figure out whether we like doing elimination, substitution, matrices, whatever makes us feel better about finding solutions for a system of equations. Okay. So let's solve this differential equation. And we're going to solve it by writing our characteristic or auxiliary equation. We're going to get r squared plus 14r plus 49 equals 0. And I think we can see from there that this is going to give us a repeated root. In fact, this is r plus 7 squared equals 0. And so we obtain a single root of r equals -7. Well, what does that mean? That means our general solution will be of the form y of x equals c1 e to the -7x plus C2 x e to the negative 7x. Okay. That's my general solution. But because I have initial conditions, I need to do a little more figuring so that I can find values for C1 and C2. Okay. Now, the first initial condition, not too bad to plug in, right? We have y of -4 equals -1. So y of -4 equals -1, which means everywhere I see an x, I'm going to put a -4. And I believe we get something like this for our first equation. -1 equals C1 e to the 28 minus 4C2 e to the 28. All right, so that's my first initial condition. But our second initial condition will deal with y prime. That means I'm going to need to take a derivative here. All right. And so that's sort of the extent of our calculus, is we're going to go ahead and use those derivatives to help us apply the initial condition. All right. And so if I write out this general derivative, the first term, I just need chain rule, -7 C1 e to the -7x plus, but when I take the derivative of the second term, I have to use product rule. Okay, so it's really important that we're like very aware of what rules we need to use. I know it's been a while since we've seen product rule, but it does come up quite a bit, especially when we're applying those initial conditions. All right, so if we take our derivative of that piece, we'll get C2 e to the -7x, and then minus 7 C2 x e to the -7x. We can go ahead and plug in y prime of -4 equals 5, and that will produce our second equation. So y prime of -4 equals, what did I say, 5? That means everywhere in here, I'm going to plug in a -4 for x. -7 C1 e to the 28 plus C2 e to the 28, and then plus 28 C2 e to the 28. Now I couldn't combine any terms before I subbed in some numbers, but after, I can actually turn this into -7 C1 e to the 28 plus 29 C2 e to the 28. All right. And so I would grab this equation, -1 equals blah, 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 blah. And I would grab this equation, 5 equals blah, 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 blah. You can do a system of equations. You can put this into a matrix, whatever. Pick your poison on how you want to solve that system of equations. And would we like to see sort of like just like substitution or elimination to set things up? Are we okay with how to solve that, or would we like to see one example? Okay. Well, if you are working through your homework and you feel like you need an example, anyone is welcome to reach out about that, okay? I cannot speak for how your linear algebra experience went or how your algebra experience went. So if you find that you're still feeling a little stuck about things, that's okay. But at the end, we should end up with C1 equals -9 over e to the 28th. And C2 will equal -2 over e to the 28. All right. And it's fine to leave those as exact values. In fact, it's actually preferred that you leave them in exact values. All right. Because once we start rounding with things, we'll end up rounding and rounding and rounding, and then things are just not quite as exact at the end. All right. But we don't want to box off those two. We want to write our actual solution with numbers in for C1 and C2. And that would be our solution. All right. So here it is all on one page. Solving this differential equation, we've actually avoided integrals. All right. So I said earlier we avoided calculus. That's not quite correct, right? We avoided integrals by using this idea that if we could solve the characteristic equation, then we can have our general solution. And then we apply our initial conditions to find our constants, plug them in, and we've got a solution to our initial value problem. All right. Now this flow, in case any of you are going to be taking partial differential equations or ordinary differential equations, this flow right here happens so much. You're just going to be looking at different cases, things that have partial fractions, or not partial fractions, but partial derivatives in them. And so it's like really cool applications of stuff. All right. So we are setting a really good foundation right now. And sometimes it's a little hard to see when we might apply it, but this kind of flow in the blue that you'll definitely see again if you take another differential equations class. Okay. All right. Well, whoops. Let's go ahead. We're going to take a look at the very last case. Okay, so far we've said everything is either factorable or we can use the quadratic formula, and every answer to a root that we've had before has been real. But in this last case, we're going to take a look at the complex roots. What happens when we get to the end of our characteristic equation solving and we end up with imaginary numbers? It turns out that our solution is going to take on a different form. Okay. So if we have our second order homogeneous differential equation with constant coefficients, just like the last two cases, we can write a characteristic or auxiliary equation. We solve, we obtain two roots. They are different from each other and they are imaginary. Okay. If that happens, we will have sines and cosines in our answer. Okay. If this happens, we will end up with sines and cosines in our answer. Our solution for ones that have complex roots looks much more different than the previous two that we saw. Okay. So let's see what this looks like in application. Solve the differential equation, y double prime plus 4y prime plus 7y equals 0. That's the same thing as saying r squared plus 4r plus 7 equals 0. Right? We have that characteristic equation. We try and factor it. It's not factorable. we are unlike Judy. We remember our quadratic formula and we start to plug in some numbers. And we realize we end up with a negative number inside that square root. Let's see if we can simplify this a little bit, just because I'm going to be plugging it into different parts of the final solution. And so we might rewrite this as -4 plus or minus 2 root 3i all over 2. And if we reduce that more, we get -2 plus or minus root 3i. Okay. Wow, I seemed a little unhappy about that problem, kind of keeps going down the page. But anyway, we have these, we find our roots, we find them to be complex roots. That should be a cue to us that we have to put our solution in this form. But if we look at our roots, we've got a lambda and a mu. All right, the lambda is going to go in the exponent with our x. And the mu is going to be a coefficient for the x inside the sine and the cosine. All right, so we have to be able to identify our lambda and our mu. That's why I took the time to simplify my answer here. So we would have this being our lambda, and then our mu would be here. Okay, so that root 3 is going to be the mu, and our -2 will be the lambda. We're going to put everything into a general solution, just like we did before, except this general solution. And maybe let me copy this. Copy. Right, so if we have this and we want to plug in, everywhere we see a lambda, we're putting in -2, and everywhere we see a mu, we're putting in root 3. We'll end up with y of x equals c1 e to the -2x cosine of root 3x plus c2 e to the -2x sine of root 3x. Right. So each case is going to give you a different kind of solution. And in the homework, I hope you'll be able to have a chance to practice what all those different kinds are and how you recognize them. I think that, you know, everyone's math trajectory is a little bit different, but if you're planning on taking more applied math classes, especially of the differential equation variety, knowing these 3 different cases will be incredibly helpful. Okay, but if this is the end of the road for you and I'm like, I am going to be a computer scientist or whatever else you are going to be, and you are not going to use those again, then it might be a little bit less important to commit to memory. Okay.
Hey, Judy.
Yeah, what's up?
What for the cosine and the general solution, would it be plus and minus the square root of 3x?
No, it's just going to be the actual like coefficient part.
Okay. All right,
So
thank you.
let me highlight this a little bit better. Just that root 3 part.
I have
Okay.
a question.
Yeah, what's up?
Is there proof for the general solution of this form in the textbook or somewhere I can find it?
I believe there is, and I know there's definitely one on Paul's online notes. Let me see if I can find it right now. He does walk through the proof. It's a little bit complicated, but if you're feeling ready to dig in, absolutely go for it.
Thank you. Okay.
Here is a link to what he's talking about, the complex roots. And he does it in a slightly different order. So he does the real roots and then the complex and then the repeated ones. Okay. And so we'll drop that one in there too for the repeated ones in case you're curious about that. All right. So
Hey, Judy.
yes, go
Hey,
ahead.
can I just ask this is maybe a silly question about notation, but every time I see in a book or on a program, everyone always writes, for example here, root 3x, which always confuses me. Is it okay to write x root 3?
Yeah, funny that you should ask because I was thinking about bringing that up. I think in general, like 3i is fine. But if you're going to do root 3, sometimes people do put the I in front so that as people, if we're writing and our root symbol gets a little long, it's not a question of is the I in the root or not. So if it's better for you to put the variable or the I in the front, that's absolutely fine.
Okay, thank you. Yeah, that's always thrown me off. Sometimes it seems like it's always under the root, but anyways, thank
I
you.
would agree. I would agree. And that is why I actually really like having LaTeX or something like that, because then when I'm typing it, I'm like, okay, like it's much more clear. It's not like my handwriting is going to go and draw that line too long and be confusing. But. All right. So let's go ahead and finish up today with this final example. And we're going to be taking a look at one more case where we have some complex solutions to the characteristic equation. And we'll have a chance to take a look at our initial conditions. And that'll be valuable because, again, if you do take more differential equations classes, knowing your trig values actually is incredibly helpful, but most of them are like work out to be super nice trig values, okay? Meaning like 1 or 0 or -1. So, all right, so we write our characteristic equation. Neither here nor there, I'm going to use an m this time, just so you can sort of see and what you like better. M squared plus 16 equals 0. Now, this is a mistake that I've seen students make before. How come it's not m squared plus 16m?
Because it's y and not y prime.
Exactly, because it's y and not y prime. And so you only, if we look at some of the other ones, everything that's with the y is just the coefficient, right? It's only the y prime that goes with like an r or an m. And so sometimes when one of the terms is missing, it's easy to sort of skip over that. And then you've got a different equation with different root solutions, and then it's all kinds of a mess, okay? So we want to make sure that is m squared or r squared plus 16, not a 16m or 16r. And we can solve this a few ways, but we could very easily subtract that 16. We're going to take a square root. We'll get m equals plus or minus 4i. Now, knowing that I have to identify my lambda and my mu, I might choose to write it like this, just for clarity inside my brain. I wouldn't judge you either way, but if you find that you tend to make, like, you're like, well, which one is the lambda? It might be helpful just to write it out. Okay. So we're going to plug things into this form. All right, everywhere we see a lambda, we're going to put 0. Everywhere we see a mu, we're going to put 4. And so we'll get y of x equals c1 e to the 0x cosine of 4x plus c2 e to the 0 sine of 4x. e to the 0, again, considered a nice number in these days because that just goes to 1. And so if I think about my actual equation, I actually have C1 cosine of 4x plus C2 sine of 4x. All right. So in this case, the way that the solutions to the characteristic equation worked out, because there's no lambda, there's actually no e as part of my solution. And that happens sometimes, right? You'll get to the solution that is just cosine and sine. Now we grab our initial conditions and we go ahead and apply those. The first one we can just take and plug in to the equation. Whereas the second one, we're gonna have to take a derivative. All right, so there's my substitution into the first one. And I'm gonna go ahead and sub into the second one, like the derivative one, even though in this case, we actually wouldn't need that to find one of the constants, okay? So we'll find that the algebra on this end is a little bit different, but the y prime of x would be negative 4 C1 sine of 4x plus 4 C2 cosine of 4x. And when I plug in my initial condition, let's see, what do we say? Y prime of pi over 2 equals 3. Negative 4 C1 sine of 4 times pi over 2 is 2 pi plus 4 C2 cosine of 2 pi. All right. Now 2 pi, no matter how we feel about our unit circle, 2 pi is the same as 0. And so this would be the same as like the starting point on your unit circle. And the starting point on your unit circle has a y value of 0. So sine of 2 pi is 0 and cosine of 2 pi is 1. And so if we apply that to the second set with the initial conditions, this will go to 0, the first term. The second term, that cosine of 2 pi will go to 1. And so it turns out that the first initial condition equation becomes negative 10 equals C1, right? Everything else either goes to 1 or 0. So C1 equals negative 10. And I don't even have to use a system of equations, okay? In the second case, the same thing kind of happens. The first term zeroes out, and we're left with 4 C2 on the right-hand side. That means that our C2 is 3/4. Okay. Now, before we write our final equation, because we do need to write a final solution, right? But before we do that, I just want to mention that this style where you set up your initial your initial conditions for your first equation, and then you take your derivative and then plug in the second set of initial conditions. The fact that one of the terms zeroes out and then you really already get the second term and you don't need a system of equations, that's far more likely to happen in like a partial differential equations class. All right. So for that reason, things like solving this system of equations or using matrices, I really leave up to you, because the reality is if you needed to find those constants, either it would be a very simple, like one of them zeroes out so you can find the other situation, or you'll have the technology to deal with it. So I'm not going to sit and have us do like a bunch of systems of equations by hand, because I think that that won't necessarily serve you well as you move forward. Okay. So if you're not sure how to set up matrices to solve these things, that would be a totally valid question to ask. I'm happy to help you figure that out and direct you towards some online calculators that might be, helpful for you. But before we tie up this question, we do need to come back and write that solution, right? So everywhere up here, we're going to replace our C1 and our C2 with the nice values we found here. And we will obtain a final solution of y of x equals -10 cosine of 4x plus 3/4 sine of 4x. This is our final solution for this differential equation. Okay. All right, so folks, how are we feeling about today's lesson? Are there any questions that are sort of coming up for folks as we finish up the end of today? And it's okay if there are no questions.
I do have one quick question. It's about what the comment you just made. If we do decide to use, if we set these up in a matrix to solve these systems of equations, and we use an online calculator, what kind of work do you need to see for that?
That's a great question. So I would say if you're going to do a matrix, just like show me what your matrix might look like, and then write your answer.
Okay, sounds good. Thank you.
Yeah, I don't need to see every little step. I trust the calculator. I trust you to use that technology. So, all right, any other questions coming up right now? All right, then I'm gonna stop this recording right here.